Hello, in this video, we're going to derive the law of cosines. To derive the law of cosines, we're going to let ABC be any oblique triangle. It does not need to be a right triangle. So we're going to choose a coordinate system, so vertex B is at the origin. And for simplicity, we're going to have the side BC be along the positive x-axis. So even if you had a different triangle, the one that was drawn here was oblique, so let's do an acute, and let's just label this A, B, and C. So even if it was sideways, I can still make this the x-axis and this the y-axis. So this is the point 0, 0. So I still set it up that way. B is the vertex, and BC is along the positive x-axis. So now we're going to let the point x comma y be the vertex of A. So right there, that is x comma y, highlighted in yellow. So now we're going to look for the sine of B. So where is B? Let's do B in orange. Here is B. B is an obtuse angle, and we know the reference angle for B is right there in orange, because D is 90 degrees, and we know that the sine of B, therefore, is the opposite, which is the y, over the hypotenuse, which is, in this case, the c. So if I multiply both sides by c, I get that y is c sine of B. Let's do the same thing for cosine. Cosine is just adjacent, the adjacent over the hypotenuse, so it's x over c. Multiplying both sides by c again, you get c cosine of B. So the x-coordinates of A are going to be, so the x-coordinate is c cosine B, that we found right there, and the y-coordinate is on the left, we found is c sine of B. And that, if we go back to yellow, is the point of A. That is A. So now let's look at C. So let C be blue. So we have blue there. And what do we have for C? It looks like it already has a coordinates because we know the distance from BC is A. So that turns out, because it's on the x-axis, as A comma 0. And the length AC is B. That's across from angle B. That will make that in green. The length of AC is B. And I don't need this right here, so I'm going to get rid of that. I just want to now use the distance formula. But before I do, I want to show you that this triangle could have been any triangle. Again, it didn't have to be a right angle. It didn't even have to be obtuse. Let's just try it with this picture over here, because this point A is still going to have these same coordinates, because I'm going to draw a line down from A, and then that's going to be my right triangle, and that is angle B still. If we call this X and we call this Y, call this X, we call this Y, you can see that X comma Y is still going to be the same values here. This one right here, by the way, this is across from C, so that's little c, and you can see that the cosine of B, or sine of B, let's do sine of B first, that we did over here. Sine of B was y over c, and cosine of B was x over c. So we still can multiply c by both sides, get that second line, and that is still c cosine of B times c sine of B. And this point right here for C in blue, this value along the x-axis is across from A, so we know that that is still A, and that point C is A comma 0. We still have this one. So we still have these two. And the distance from AC is across from the B, so that is still B. So we're going to just construct that with B being on the vertex, A being on the x-axis, and the following are true for angle B, whether it's obtuse or acute. So now let's go ahead and use the distance formula to find a formula for this situation. If you remember from algebra, D is equal to the square root of x2 minus x1 squared, y2 minus y1 squared, where x1 comma y1 and x2 comma y2 are 2 points on a plane, or D equaling the square root of the quantity x2 minus x1 squared plus y2 minus y1 squared is the distance between 2 points x1, y1 and x2, y2. So we know that we're going to look for the distance of B. So let's let D equal the B. And I'm going to erase this and let my first point be the point C, and my second point, point C, and my second point be my point A. So I want to find the distance there. And I'm just going to plug this in. So we have here x2 minus x1. So here is x2 and here is x1. So I'm going to subtract those. x2, which is cosine C cosine of B, minus x1, which is A. Plus, now I'm going to do the same thing for the y2s. y2 minus y1, here's y2, here's y1 in green. So let's go ahead and write that. y2 is C sine of B, don't forget about that C, minus 0 squared. The first thing I'm going to do is get rid of the radical by squaring both sides. So I'm going to have B squared is equal to C cosine of B minus A. At the same time, I'm going to rewrite this as what it is, C cosine of B minus A. Because I'm going to multiply that out and I want to get rid of that squared there. This one, I'll just subtract that 0. We won't count that. So we can call it a C squared times sine squared of B. So now I'm going to use FOIL to multiply, get rid of the parentheses. So we know that B squared is going to be C squared. First is C, the first here is C squared cosine squared of B. And then the outer terms, that would be minus AC cosine of B. The inner would be another minus AC cosine of B, so I'm just going to have 2 of those, plus A squared plus C squared sine squared of B. Now I see the fact that cosine squared plus sine squared is 1. So I'm going to bring these together to use that idea. Actually, first I'm going to write the A squared first. Then I'm going to do the C squared cosine squared of B plus C squared sine squared of B. And then I still have this minus 2AC cosine of B I'll put on the right. I can factor out a C squared in the second and third term. And then we get that cosine squared B plus sine squared B, which we know is 1. So we have it. B squared equals A squared plus C squared, because this is just 1. Again, cosine squared plus sine squared in blue there is 1. And then what's left is minus 2AC cosine of B. This formula is one of the forms of law of cosines. This result is one of 3 possible forms of law of cosines. In our work, we could have easily have placed A or C at the origin, and this would have given us the same result, but the variables would be readjusted. So if this was C, if I switch the C and the B, let's do that right here, this one, switch the C and the B, we would have that C squared equals A squared plus B squared minus 2AB cosine of C. That would be another form. And then if we did the other switch, put A at the vertex, you're going to get something like A squared equals B squared plus C squared minus 2AC cosine of A. Oops, there's a little mistake here. This should have been AB. So how I always remember this is the one that is on the outside here is the same as the angle. And it's going to be kind of like the Pythagorean theorem. It's kind of like the hypotenuse, isn't it? If the B is 90 degrees, it would be, we'll talk about that in a second, a right triangle. And so you would get the Pythagorean theorem. But when it's not, then you have the other 2 squared, and then the AC is here with the cosine of the same angle. Same with this one. C squared is the other 2 squares, minus 2, the AB that's here, and then cosine of the same angle that's alone. And this one, B squared plus C squared minus 2BC cosine of the A. And you can see here that if C is 90 degrees, we'll put C in the vertex using this one. You would have C squared equals A squared plus B squared minus 2AB cosine of C, big C. This will be little c, this will be little b, this will be little a, and you would have C to be 90 degrees, which is what we usually do. We let C be the 90 degrees when we have a right triangle. And if C is 90 degrees, you can see that you just have the Pythagorean theorem. Cosine of 90 degrees we know is 0. So you get C squared equals A squared plus B squared. So this is the case of a right triangle where the C is 90 degrees. And that's the formula that we have been using since the beginning of the course for a right triangle, the Pythagorean theorem. So this is just an extension of that, isn't it? So that concludes how you get law of cosines.